Hey, Algebra 2. We're working in Chapter 3, Section 5. The warm-up here, I know some of you guys skip, but this is reviewing stating domain and range for quite a few problems, so I would recommend you working through these and reviewing how to figure out what a domain is and what a range is. Okay, this first one, state the domain and the range. A little review. Domain is your input, what you can plug into an equation, which is also your x values. Not all equations allow every single x value to be plugged into it. So you sort of have to think about what is allowed. If negatives are allowed, if zeros are allowed. So that's what you have to think about. And then range is your output. What comes out of the equation, what it equals, your y values. So this one is a line. It's actually a line that crosses the y-axis at -5. If I look at my x values that are allowed, I can look at my x-axis and then sort of carry down like, oh, I can have lots of negative x's and I get a value. I can have lots of positive x's, I can get a value. I can even have a 0 for an x and I get a value. So for this one, our domain would be all real numbers. And then I can look at the range. The y values, here's my y-axis. I can look at lots of positives, lots of negatives, and I'm even allowed a 0. So my range would be all real numbers. Hold on, I need to go let the dog out. Does anybody else sing Who Let the Dog Out when I said that? Yeah, we sing that all the time in the house. Now this next one, this is a parabola. This is where you really need to know your parent functions too. It's a parabola because it's squared. That means it's a happy U-shaped up or down. Negative in front means it opens down, and the +6 means it starts at 6 above the x-axis. 1, 2, 3, 4, 5, 6. So it looks kind of like this. So if we look at our range, our domain, which is our x values, it's going to be all x values, like every single x value that I plug into this equation, I'm going to get an answer. So my domain, is going to be all real numbers. But my range, I will never get, my range is going to be below, inside the parabola. It will never be above the happy part, or the sad part. So my range is going to be y values less than or equal to 6. With practice, we'll get the hang of it. Okay, gets a little bit harder. Okay, this is definitely an Algebra 2 problem. So here I have a parabola again. Okay, it opens up and it starts at -8. So it would look like this. So it goes down 8 and it's happy. So my domain, again, is going to be all real numbers. Every single x value in the number line is allowed to get plugged into this value. So my domain is all real numbers. Now my range, hopefully you get the hang of this one because we just did this one like this, but it was a sad parabola. My range, my y values that are going to be output is just there, not there. So my range is going to be y values greater than or equal to 8. -8, sorry, because we went down. Graph this graph and state the domain and range. Compare the graph with y equals the square root of x. Let's see. 1, 2, 3. 1, 2, 3. All right, I'm going to do a little t-table. If I plug in 0, I get 0. If I plug in y, I actually get 0.5. Sorry, I plug in 0, 0. I plug in 1 for x, I get 0.5. I plug in 2, 0.71, 3, 0.87. If I plot these, I'm going to go here, 1.5, 2, 0.7, 3.8. All right, that one was, we'll make it all red. This was the 1/2, y equals 1/2 root x. If I compare that with, well, let's do a different color, blue. The original function, I'm going to get, 2 square root. So plug it in, 1, 1.41, and then 3, 1.73. Sorry, I'm moving a little slow. 0, 0, 1, 1, 2, 1.4, 3, 1.7. So when we talk about domain and range, we really have to think about what we can plug in for domain, what's allowed. We're not allowed negatives, remember? We can't take the square root of negative and have a real number. That's where things get imaginary. So our domain here is going to be values that are positive. Our range is also, because if we only put positives in, we're only going to get positives out. So our domain, our range is also positives. But what I'd like to show you is the graph of y equals 1/2 root x is a vertical shrink of the graph y equals root x. Dog's whining. Sorry, chaos in the Shellhammer house today. So the graph of y equals 1/2 root x is a vertical shrink of the graph of y equals root x, that's this mess right here, by a factor of 1/2. Cool? Oh, I put it in there. All right, so graph y equals -3, cubed root of x, and state the domain and range. Compare with y equals the cubed root of x. Hold on. Now, this is a cubed root. You remember in cubed roots we're allowed to have negatives. So as I test points to graph, I'm going to put in some negatives too. So really we know here that my domain is going to be all real numbers, right? That also means if I plug in all real numbers and I can have negatives, my range is also going to be all real numbers. So all the values I can plug in can be anything, and all the values that I'm going to get out are going to be anything. So if we plug and chug some numbers, -2, I've got 3.78, -1 is 3. Check your calculator out, works pretty well. Use some parentheses so you don't lose your negatives. And if I graph this, I'm going to have -2, 3.78. So -2, 3.78's up here somewhere. -1, 3, 0, 0. And then 1, -3, -2, -3.78. So it looks kind of like this. And if we plug in, so that was that one. Oh, didn't want to do that in blue. Now let's go ahead and try the original. All right, I plugged in for the original function in blue. Let's graph it. -2, I have -1.26. Right about there. You really can't see this. There we go. -1.26, about right there. Nope, I was positive. There we go. -1's going to be -1. So really I need, in my awesome graph, this to go just a little bit further down. +1 would be +1. +2 would be +1.26. So we look a little bit like this. Sorry, you hear my dog getting comfortable. All right. All right, you're going to see this on the next slide, but I'll talk through it first. We already talked about the domain and range being all real numbers. The graph of -3 cubed root of x is actually, oh, for goodness sakes, changing my pen, a vertical stretch. By a factor of 3. And then a reflection. That negative right there gives us a reflection. And there it is. The period of a pendulum is the time the pendulum takes to complete one back and forth swing. This is a number. The period t in seconds can be modeled by t equals 1.11 the square root of L, where L is the pendulum's length in feet. Okay, got a clock pendulum, I guess. It's sort of held up here and it swings left and right. The period is the time it takes to complete one back and forth swing. So even if I start here, back and forth. No, that's not right. It would be back and forth. Back and forth. So wherever it starts, it has to go back to the spot. I guess we could do this one also. If we started here, back and forth. It has to be one complete rotation, but it's not really a rotation. It's a complete swing. And then the length of your pendulum is that value right there. Use a graphing calculator to graph the model. How long is a pendulum with a period of 3 seconds? So I've got time equals 3, 1.11 the square root of L. Divide both sides by 1.11. That was awesome. So the square root of L equals 3 divided by 2.703. Take this, or square both sides. 7.30 feet. But let's look at our graph, which I have on the next page, and see what it says. I solved it algebraically, but let's look. So first we graph the model and enter the equation into the y equals, right? And then you can hit the graph button. If you don't remember how to do this, please yell and I will show you in class. Cool? Then use the trace feature. The trace is a button right underneath the screen. We've got the screen. The trace button is right there. Just push it. And then you can arrow left and right. And this little, I've always called it a spider, will just travel along your graph and try to get to where y equals 3, read your x, 7.31, which I got 7.3 when I did it algebraically. Cool? So the answer, the pendulum with a period of 3 seconds is about 7.3 feet long. So let's graph the function and state the domain and range. Okay, I've left the graph that the book put in because it's a lot easier than you trying to read my graphs. But if you plug in, I mean, this is the square root, so the domain I'm going to test is going to be 0, 1, 2, 3. And I'm going to plug that in and get my answers. This is a reflection over the x-axis because of that negative. So that's why our graph goes down. Oops, wrong button. Right? So what's our domain? We can't plug in negative numbers, so we have to say it's positive by saying x is greater than or equal to 0. And the range is actually negative. Y is less than or equal to 0 because of that negative right there. And you would see that as you graphed it, because remember the range is our y value. So if I look at the y-axis and see where the graph goes, I have no y values that are positive. All right, graph it. Again, oh goodness, x, y. It's still a square root, so all the x's that I'm testing are going to be positive, and I can get the y values that come out, our output, our range. So for x, we're going to have our domain. X is greater than or equal to 0, and our range, because we're positive, this right here is positive, our range is going to be y is greater than or equal to 0. And we have our graph, which is all positive numbers. Okay, cubed root, so I can get negatives, and it's a reflection over the x-axis. So I've got x, y. I'm going to test negatives just like I did in the practice problem. And I'll see what my graph will look like. So my domain here is going to be all real numbers. And that's my input. That's what I'm allowed to put in. I can put anything into a cubed root, which means I'm going to get anything out of a cubed root, all real numbers. Okay, I have another cubed root. So same deal. Go ahead and plug in your x and y with negatives and positives. And because I'm a cubed root, my domain is going to be all real numbers, and my range is going to be all real numbers. What if? Use the model in example 3 to find the length of a pendulum with a period of 1 second. You can do so graphically or algebraically. The equation, let me look it up. We had t equals 1.11 square root of L. If our time is 1 second, not 2, we would divide both sides by 1. Oh, I did it again. 1.11. 1. I get 0.901 equals the square root of L. Square both sides, I get 0.812 equals the length. But let's graph it and see. And if you look here, I plugged in my equation into y equals and I hit graph, and then I hit the trace button, and you'll see that spider sort of going along the the graph because I'm using the arrows to make it move. I stopped the spider at 1.02, which is about as close as I can get to 1. And I have an x value of 0.85, which is decently close. All right, we have the end of the lesson. Remember, these are the ones that we can practice, and they're great practice. Remember, here we have a cubed, so our domain can be all real numbers, therefore our range can be all real numbers. And here is the pendulum problem for practice. The book seems to like to graph it and trace it to find the answer. I'm all about the algebra to find the answer, so you can do what you would like. Today's lesson was a little bit truncated for lesson 5, but you guys are getting the stuff that I need you to learn, so I'm not so worried about it. Enjoy the truncated version. All right, good work.